Hello, good evening, and thank you so much for inviting me to be here. I've been in Auckland since the beginning of March, and I'm heading back home to Seattle in the States in just a couple of weeks. So I'm really glad that I got the chance to come visit and come give a talk. And what I'll be presenting about tonight is, as was mentioned, my book on, this is the trick, you always carry a copy of your book, on what it's like to be a professional astronomer, and what it's like to have this very unusual job and basically stargaze for a living. And my book came out in the middle of 2020, which is the worst time to possibly release a book. But before the entire planet shut down, I got to go to one or two book events where I was talking to other authors and getting the chance to sort of meet with audiences and answer questions and just share our books. And a topic that came up in one of these sessions was famous first lines of books. And there are iconic first lines that you just get burned into your memory. So, you know, call me Ishmael for Moby Dick, or it was a dark and stormy night, which is how A Wrinkle in Time begins. And the other authors started talking about their first lines. And it got me thinking, okay, well, this is a book about really traveling to the edges of the planet to solve the mysteries of the universe and the wild adventures that astronomers have when we do this professionally. So what's the opening line that sort of welcomes people into all these amazing adventures? And the first line of my book is, have you tried turning it off and on again? Which we just lived in Technicolor getting ready tonight. So this doesn't sound exciting. This sounds like, you know, sitting in a room waiting for a presentation to start. It sounds like every phone call you've ever had when your internet stops working. But this is the most terrifying thing that's actually ever been said to me at a telescope, because I got asked this while sitting here. I was sitting in the control room of the Subaru telescope near the summit of Mauna Kea in Hawaii. I was a graduate student. I was using this telescope for observations for my PhD thesis. I was trying to study the galaxies that had hosted gamma ray bursts. So these brief, bright flashes of gamma ray emission that accompany what we think are really strange, bizarre, rapidly rotating dying stars. I was in the middle of observations for my PhD, sitting in the control room of this telescope, when one of the computers in the room made this sort of like blunk sad sound. And I looked over at the computer, and then I looked at the only other person on the mountain with me, who was the operator trained to run Subaru. And she looked at me and said, I think that sounds okay. And I asked for a little more information, and she said, I think we're fine. I think the mirror is still on the telescope. This was not reassuring because I didn't know that mirrors could come off. So I asked her to explain. And to give you a sense of scale, when we say the mirror's coming off the telescope, that's me down at the bottom of the screen standing under another mirror about the same size as Subaru. Both of these mirrors are a little over 8 meters from end to end. So when we were talking about the mirror that was falling off, it wasn't quite this mirror. It was the mirror suspended high above the primary. So this is a different telescope. This is Palomar in California. And you get a nice view of where the primary mirror of a telescope would be. In this case, it's sitting near the bottom of the screen so that it can point upward and catch the starlight that's coming in. There's also the secondary mirror suspended high overhead. The blunk sound had been telling us that the secondary mirror of Subaru was no longer being supported. The mechanical structure that was holding it up and that was supposed to automatically adjust how much weight it held had failed. So the blunk was telling us that if we tipped the telescope too far to one side or the other, the secondary mirror would go sliding off and plummeting down to the concrete floor of the telescope dome. If we were lucky, if we weren't lucky, it was going to hit the big mirror on the way down. So we put in this very nervous phone call to the daytime telescope crew asking what to do. And they very cheerfully said, oh, you're probably fine. It's probably a false alarm. That's probably the same problem we noticed earlier today. They kept saying probably. You can probably fix this problem by turning it off and back on again. And it really seemed impolite to say, you know, that's how I fix the internet in my house. I don't really think this is how I fix the telescope the size of the building. So this then left me trying to decide what to do. And I just kept having stories running through my head of things that had gone horribly wrong at telescopes. And the most memorable one was a story I'd heard about this telescope in West Virginia. A couple of people are nodding because they know what's about to happen in this picture. This is the beautiful Green Bank radio telescope in West Virginia that was operating and doing some of the best radio astronomy in the world in the 1970s until one evening when this telescope, mid-observation, went from this to this. So this story had become infamous in the astronomy community. I couldn't remember what had happened. I assumed someone had tried turning it off and on again. So I was then asked what I wanted to do. I was just a grad student, but I was in charge of this telescope. I was the one running it. I desperately needed to keep observing for my thesis. If it was a false alarm and I canceled early, I would lose really precious data. But if I kept going and it wasn't a false alarm, I was about to be the grad student that killed Subaru. So I had to decide what to do. And I use this story to open my book because it's a glimpse at how things can go wrong and sort of the stories that follow us around when we work in astronomy. It's really not hard to get people excited about space. Everybody loves the beautiful pictures of space that you get from Hubble or Webb or the beautiful amateur photographs that you get. It's not hard to sell people on the romance of space. But what they know less about is what astronomers actually do, what our jobs actually entail, and the backstories behind pictures like this. I think if you asked most people to picture a professional astronomer, they picture something very familiar and similar to the backyard astronomy that they might do. They picture usually a man. He's usually got a beard, apparently. He's wearing a lab coat for safety reasons, and he's standing next to a little telescope that he's looking through with his eye. And it's a fair picture because this is the experience that most of us have when we first start getting interested in astronomy. When I was a really little kid, this is me when I was 6 years old, I knew that I liked space. I knew that I wanted to be a scientist of some kind. This is me proudly sporting my Hubble Space Telescope t-shirt. And my experience with astronomy had been a little telescope in my backyard that I went and worked at with my dad that we would peer through with our eyes. So when I imagined being a professional astronomer, I just pictured a more dramatic version of that job. Growing up, this was what I thought science was. I didn't know any scientists. Nobody in the town where I grew up had a PhD. Nobody did science for a living. I mostly learned about science from movies. Based on these movies, I figured your science spent a lot of time chasing you. I also knew that you probably didn't discover aliens every day like Contact made it look like, so this was the most that I knew about my planned-on career until I was actually halfway through college. After the summer of my second year at MIT, I got to go here. I got to visit Kitt Peak National Observatory in southern Arizona and work with a research advisor on a project for a few months. We traveled to Kitt Peak, and this was my very first time at a professional observatory. We stopped in the dormitory, we dropped off our things, we went into dinner, and we sat down at a table with a bunch of other astronomers. And my advisor introduced me. He said, "This is Emily. She's a brand new student. This is her first time at a professional observatory." And all the astronomers said, "Well, this is fantastic. Welcome. Have a lot of fun. Start drinking some coffee so that you can stay up all night, but remember to stop drinking it at about 4 or you'll never go to sleep." And then someone else said, "Remember to order your night lunch, the meal that you have in the middle of the night, from the kitchen. They'll deliver it to the telescope and then you eat some food at midnight and it helps keep you going." And then someone else said, while you're at the telescope, remember to kind of watch your feet because we have scorpions in this part of Arizona. There was a woman who was observing who had a scorpion crawl up the inside of her pant leg and sting her while she was at the telescope, and everyone at the table kind of did this and picked their feet up. And someone else said, "Well, I know a guy who was observing back when you were in the dome in the dark, and he had a raccoon crawl into his lap, and he just pet it until it fell asleep." And then someone else said, "Well, I know a guy who was in a dome when it got struck by lightning." And someone else goes, "Well, I know a guy who was at a telescope when it got shot." And the stories just kept going on and on. That's true, by the way. The stories just kept going around and around the table. And I was sitting there frozen with my fork halfway to my mouth going, I don't know if I want to stay here all night and just listen to these people tell stories, or if I want to go running off to a telescope and see about getting some stories of my own. So years and years later, that first dinner and that sort of welcome to astronomy is what stuck with me. And that's what gave me the idea for my book. So it uses these stories of what it's like to work on a mountain to give readers this sort of behind-the-scenes tour through the adventures of professional astronomy and a glimpse of what it's actually like to do this job. So for researching this book, I got the chance to travel around to some amazing observatories in the United States, in Chile. This picture down here is sort of in Christchurch, and I'll explain that in a minute. I got the chance to visit all these amazing facilities and learn a lot about the history of the field. The most interesting thing that I got to do is actually this picture on the lower right. It looks boring, but that's actually my trusty voice recorder. I used this to record interviews with more than 100 of my fellow astronomers. I talked to colleagues who were brand new graduate students. I talked to colleagues who were in their 90s, and I tried to gather as many stories as I could about what their jobs had been like. I'm not a trained reporter. I'm not an investigative journalist, and I was learning on the fly how to conduct interviews. And I learned quickly that the best way to get these stories was usually to just let people talk. But there were a few questions that I asked everyone. I didn't want the book to just be a collection of anecdotes. I wanted it to follow a storyline and sort of follow the evolution of the field and have these sort of common human threads of what astronomers' experiences had been like. So there were 3 questions that I asked everyone. And I'm going to use these questions to sort of frame what I'm presenting to you tonight. The first question that I loved asking was, what's your most memorable sort of second or third or like 10th hand observing story? This wasn't anything that had happened to someone directly or anything they'd been present for. I wanted the story that they'd heard retold after a conference over beers from a guy who heard it from a guy who half remembered. I wanted to hear the stories that had almost become tall tales in the community. I wanted to do this so that I could hopefully track those stories back down and get the true versions in my book. But I wanted the stories that astronomers loved telling each other. And there was one answer that I got over and over with this question. And it was sort of connected back to, there were these weird bursts of radio light, and we thought they were one thing. They turned out to be something else. This was somewhere in New Zealand. The people were half remembering the story. And I finally tracked down the real one. This was at Parkes Observatory in Australia. They were close. But what this actually was a very strange observation that began in the mid-2000s at the Parkes radio telescope. So in the middle of observing that one evening in 2007, there was this brief flash of bright radio emission that caught the observatory by surprise. They hadn't expected to detect anything like this. This wasn't something theory had predicted. It was earmarked and set aside as, well, that was strange, that was unusual, we don't know what that was, and people moved on. Years later, a young woman named Emily Petroff arrived at Parkes to do her PhD thesis, and she wanted to study events like this. She thought she might be able to start exploring what phenomenon could explain this brief flash of radio light. And when she told the observatory she was doing this, they immediately said, no, don't bother. We detect these sorts of things all the time. We don't think they're interesting at all. We're pretty sure that what we're detecting is just radio interference. There's no science there. That's a terrible thesis. Don't bother. They had actually detected these so many times that they'd given them a nickname. They had started to call these events peritons, which are mythical creatures that look like one thing but cast the shadow of something else. It's casting the shadow of real science, but it's really just some other radio signal. Talking to them, Emily realized that everyone assumed these were coming from some sort of interference source on the ground, and she decided the only way to get to the bottom of this and decide if there was really a thesis in there was to explain what peritons were, which nobody had been able to do for years. She actually wound up rounding up the entire staff of the observatory. So on the paper she eventually published with the answer, it's the only paper that I know of that has the secretarial staff, the janitorial staff, everybody who works at the observatory as an author, because everyone had to get in on solving the problem. And their first hint when they started looking at these data were that peritons tended to show up at the telescope around lunchtime. And space is very strange, but space does not care when lunch is in Australia. So this was their first clue as to where they might be coming from. If you look at this aerial view of the observatory, you can see 3 buildings marked with arrows. Those are 3 administrative buildings where they have offices and break rooms. The break rooms have space for people to make coffee or tea or to heat up some leftovers in a microwave. And the microwaves were what they homed in on because they thought that these signals could be coming from a microwave being run on site while the telescope was turned on. In the paper that they wrote, they are so careful. They describe exactly how these microwaves work. Some poor soul definitely read the entire manual for some terribly outdated microwave that was sitting in a back room at this observatory. They ran them on high and low power. They ran them for 10 seconds or 60 seconds. They always microwaved a ceramic mug of water. They were such careful scientists about trying to test this idea, but it wasn't working. They would turn the telescope on, run a microwave, turn it off, check the telescope, and there was no signal at all. And finally, someone realized that they were victims of their own carefulness. They were being good scientists and running the microwave, waiting, and then checking the telescope. And that's not how we use microwaves, because when you heat up a takeaway, you turn the microwave on and you watch it count down, and you're hungry, and you're going 5, 4, close enough, and you open the door, you know you do it, while the microwave is still running. And you stop the microwave by opening the door. When they did that, when they opened the door while the microwave was still running, they did it. They were able to produce a periton and explain this strange signal that Parkes had been picking up. So they went back to the data and realized that all of those weird detections that they'd been finding for years could be explained by impatient snacking, except that very first one from 2007. Now that they knew what to look for, they could tell the difference between weird signals from microwaves and actual strange brief blasts of radio emission from far away in other galaxies. Today, there's an entire subfield that studies fast radio bursts, these weird brief radio phenomena, but we never would have had this if we hadn't first, discovered microwaves in our pursuit of trying to explain what Parkes had been doing. So many of my colleagues told me this story or some version of this story because I think they liked the idea of these mistaken detections, or of scientists being tricked or having to dig through sort of weird signals to arrive at a fairly pedestrian solution, like a microwave. The favorite version of this that I got told is actually a story that I heard after the book came out, so I was very sad that it didn't wind up in the book, but it also takes place in West Virginia, where I showed you a picture at the very beginning of the talk. This is the beautiful new telescope that has replaced the collapsed telescope you saw. They rebuilt this telescope in this particular part of the United States because it's a place known as the National Radio Quiet Zone. It's actually an area where radio emission from things like microwaves or other interference sources is severely dampened. Nobody living near this observatory has a cell phone, has Wi-Fi. If they do have a microwave, it's in a special cage so that it protects any errant signal from getting out. The vehicles that drive to this telescope actually all run on diesel because the sparks from a spark plug in an internal combustion engine produce tiny bits of radio signal. They keep this area perfectly radio quiet so they can take some of the best radio observations on the planet. And this works great most of the time. You can also see the really beautiful forest around the telescope itself. And this forest is home to a really beautiful, diverse natural habitat. It is home to a population of these very interesting little flying squirrels. And some environmentalists decided that they wanted to study these squirrels and keep careful track of their movements. And the only way you can do this is by fitting them with little radio collars. So they unleashed this adorable swarm of radio interference sources by catching and releasing tons of little flying squirrels. So these little guys pretty much shut down the telescope for 2 to 3 months. They would try to get observations of, a supermassive black hole at the center of a galaxy. Nope, squirrels. They would be trying to do some radar research. Nope, still getting squirrels. They pretty much had to shut down, do engineering work for a couple months, and wait for the batteries and the little collars to die before they could keep going. So people had all sorts of whoops, we accidentally detected so-and-so stories. And you can imagine this happening with radio interference, where a cell phone or a microwave can cause problems. You can even imagine this happening in the visible light range. Any sort of interference source, like headlights passing over a dome or a match getting struck near a mirror, all of those things could also cause interference. A surprise is that you can even do this if you leave light behind entirely. We have this same problem at gravitational wave observatories. So to briefly describe what these are, this is one of the 2 gravitational wave observatories in the United States. This one is in the Pacific Northwest. And the way that these observatories work is that you have these 2 perfectly straight vacuum tubes stretching, I think they are 4 kilometers apiece. 2.2, yep, 4 kilometers each. And what they'll do is they send these little laser signals down each arm to very, very precisely measure the length of the arm. Normally, this does exactly what you would expect it to do. Each arm is exactly 4 kilometers long. The laser travels down and back at exactly the expected amount of time, and you get 2 laser beams come out, 2 laser beams come back. They arrive at the same time, and there we go. This stops happening if a gravitational wave passes by Earth. So a gravitational wave is a compression wave in the fabric of space-time. So when it passes through the space-time where our Earth is, you get this squeeze and stretch in the Earth on a very minute level. The difference is something like 1/1000th the width of a proton. But incredibly, this detector is capable of picking that up, because even that tiny little compression, and I'll way exaggerate it in this image, but even that tiny little change will mean that when you send those 2 laser beams down those 2 arms, they will travel at slightly different times, they will arrive back at slightly different times, and you get a signal saying, wait, a gravitational wave has just passed by. These have been very slightly perturbed. You're detecting this ripple coming from, 2 enormous colliding black holes far, far away in our galaxy. These work amazingly. These observatories took decades to develop, and they're capable of detecting, like I said, these minute differences from colliding black holes, showing us the ripples in the fabric of space-time. The problem is they also detect everything else. So much of the challenge of a gravitational wave observatory is stopping it from detecting these errant sources of signal. They only let tours go to this observatory on certain days of the week because people's footsteps will ring the ground for hours and leave behind errant signal. They can detect trucks driving by on a highway that you can barely see in the background of this picture. They can detect waves hitting the shelf of the Pacific Ocean at the coast 200 miles away. They detect rain. They detect everything. For the most part, the observatory has now gotten good at getting rid of these, but there's still 1 or 2 issues. They started getting this weird errant signal once in a while in the detector that they couldn't explain. It wasn't rain, it wasn't footsteps, it wasn't a truck. And they eventually figured out that there were, on the outside of the vacuum tubes, these very weird peck marks. Now, you can see from the picture, this is in the middle of a desert. In the summer, it gets very hot. They have to cool these vacuum tubes by running coolant tubes to them, and those cooling tubes will accrue ice on the outside. So there are these weird little peck marks showing up on the outside, and they were getting these strange little signals whenever these marks showed up. Someone eventually realized that this guy, who got nicknamed Thirsty the Raven, was pecking at the ice. This was just a very convenient drink on a hot summer day. And they suspected that the little poke, poke, poke was enough to mess with the signal from the observatory. They actually, again, being good scientists, they tried to replicate this, so they sent out a grad student to pretend to be a raven and knock on the pole with a hammer, and they were able to successfully prove that that's what they were detecting. So they had a bird mimicking colliding black holes, but they had at least figured out how to account for and then get rid of another source of noise in the observatory. So these were the stories people loved telling me, these sort of half-remembered tall tales of when astronomers made mistakes. Another question I loved asking is what they thought would surprise people the most about our jobs. What was the biggest disconnect between what people think professional astronomers do and what we actually do? A lot of people had some explanation of, we don't look through eyepieces anymore. Our job doesn't look like this. We go to these telescopes the size of buildings. All of our data comes in on computers right now. But it wasn't necessarily just we don't look at our data with our eyes anymore. It was, our jobs can get a lot wackier than people think. We have some really incredible adventures in pursuit of trying to do our research. And I heard so many wonderful adventure stories from people that had traveled all over the planet and gone to incredible extremes to do their research. I talked to astronomers who had traveled all over the planet in things like flying telescopes, which I'll get to in a minute, who had studied things like solar eclipses and traveled with gear all over the world to track the path of an eclipse. Who had traveled down to the South Pole to launch instruments on board balloons. We had just such an amazing mix of different stories that we got. So the flying telescope that I showed back there, I need to back up a slide, is NASA's Stratospheric Observatory for Infrared Astronomy. This is SOFIA for short. It is a plane that runs an infrared telescope out of its back door that's able to open while it's in the air. It flies up above all of the water vapor in our atmosphere so that it can then detect light that you normally couldn't get at from the ground. So as part of my research in studying stars and how stars die, and in part of my research for this book, I actually got to fly on SOFIA during one of its flights from Christchurch International Airport. It flies out of here during the Southern Hemisphere winter to take maximum advantage of the dark winter skies and fly around the Pacific. We actually flew so far south on that particular flight that we got close to the Antarctic Circle. We were able to see the southern lights from the plane, sitting in an experimental plane looking at, this was the first time I'd ever seen the southern lights. This was one of the coolest adventures I'd ever had in astronomy. I spend an entire chapter in my book talking about this flight and about the many other flights that people have taken in pursuit of trying to put telescopes in planes, because this is a surprisingly rich observational history. So that was one of the coolest adventures I ever got the chance to have. I also talked to people who sent observatories, like I said, aloft on balloons from places like the South Pole, who traveled to chase eclipses, who observed with permanent telescopes at the South Pole. So I was talking to folks traveling all over the planet for astronomy. I also got to hear the story of this particular researcher. So at a glance, it looks like I lied. It looks like this is a guy standing next to a little telescope in a lab coat. He has a really good reason, though. This is George Carruthers, and he is the inventor of the ultraviolet camera. The same technology that we have on the Hubble Space Telescope, allowing it to detect ultraviolet light, is based in George's inventions. He's standing next to the first telescope that really used what he had invented, which is a seemingly tiny little 4-inch ultraviolet telescope. But the reason this telescope is so fascinating is it's the only telescope we've ever taken to the surface of the moon. This telescope flew to the moon on Apollo 16. The astronauts operated it for 3 nights. They pointed it at stars for the first time, back at our own Earth. We got to see our first view of the ultraviolet universe. When I was writing this book, I had to start limiting what sorts of stories I was telling, because if I took every single story that every astronomer had told me, I would have a 1,000-page book. And I decided I needed to stick to observing that happened on the ground. I wasn't going to be telling stories of using Hubble or Webb or all of these other space-based telescopes, just because it's a really different kind of research. I decided that this telescope was an exception because it's technically on some ground. It's not on our ground, but it's at least sort of ground-based astronomy. For these 2 astronauts, it was for a little while. So these are some of the adventures that I got told about just how far-flung astronomy got. I also just heard a couple wild stories about things that could happen when you were working at observatories out in the middle of nowhere in some of the most naturally beautiful but also interesting parts of the planet. This particular story happened at Monastash Ridge Observatory, which was also in the Pacific Northwest, and it happened at this little telescope that my university, the University of Washington, normally uses to train graduate students. In 1980, there was a graduate student working at this telescope named Doug Geisler, and he was, again, doing research for his PhD thesis. This seems to be something of a theme in all of these stories. Everyone's best story happened during their PhD. He was working at this observatory, getting his first round of data for his thesis and taking very careful notes in what we refer to as the night log. So back before everything was kept electronically, there was this big book at the observatory, and you would fill out all these little details where you would fill in the date and say how many hours you observed. You observed from 10 p.m. to 4 a.m. You observed for 6 hours. The sky conditions were excellent. He lost 0 hours of time to bad weather because it was an excellent night. And then you sort of write in notes saying the clouds cleared off, I had a beautiful night, everything went great. When life is going well, this is what you want your log entry to look like. And this was what Doug's first log entry looked like. He then went to bed early on the morning of May 18th, 1980. And this date doesn't mean anything to almost everyone, but whenever I tell this story in the Pacific Northwest, there's someone in the audience that goes, because they recognize what happened that day. Later that morning, Doug woke up and he heard this sort of weird, very vague, sort of like distant rumbling sound, and he went, that's weird. He was exhausted from observing. He went back to bed. He then woke up for the day around noon and opened the door of the dormitory expecting to be blinded by sunlight, and instead he opened the door into absolute blackness in the middle of the day. There was this awful sort of brimstone smell in the air. He grabbed a flashlight and tried to point it out the door, and the flashlight beam got swallowed after a few feet. It's 1980. He thought he was living through nuclear war or the end of the world, and went running back into the building. He can't, check his cell phone for a news feed, so he's trying to tune in a radio to get news on what's happening. And he finally found out that earlier that morning, Mount St. Helens had erupted, one of the biggest volcanic eruptions that we've had since, since we've been keeping modern track. He realized what had happened then, because Mount St. Helens is to the southwest of the observatory where he was working. And if you study this eruption, you see that the side of the mountain effectively blew off. So this is what wound up happening. When Mount St. Helens erupted, the eruption blew a plume of volcanic material directly over Monastash Ridge and directly over Doug. So this is what he was standing in when he opened the door of his dormitory. He very carefully ran out and covered and closed the telescope because he knew that he didn't want the corrosive volcanic ash falling onto the mirror. And he then very carefully took some notes in the logbook. Hours lost, 6. Reason, volcano. Sky condition, black and smelly. Comments, I am the last survivor of the war. So this log entry is still sitting in the book up at Monastash Ridge Observatory. It's the most dramatic by far record that we have of observations that got completely derailed by something like a volcano or some sort of natural disaster. So the last question that I asked everybody as I interviewed them was how astronomy had changed since they began observing. I mentioned that I talked to colleagues who were in their 90s. We had a beloved colleague at the University of Washington who had spent 30 years observing using glass photographic plates and then 30 years observing with traditional digital plates. It was fascinating to talk to him about the shifts he had seen in his career. So when I mention a photographic plate, this is a great example of what one of these tools looks like. I wish I had one with me to show you. I wasn't able to get one from a plate archive to bring tonight, but these look like thin little tiny sheets of glass. They almost look like they could break if you look at them wrong. They are chemically treated on one side to darken when exposed to light. And back when people were using this to observe, they would order crates of these plates. They would painstakingly cut them down to a size that fit into their telescope's camera. They would do all sorts of chemical tricks to them to make them extra sensitive to light. They would then load them into a camera in the dark and shiver next to their telescope for hours, exposing this plate to no light except the light from a faraway galaxy or a star that they were interested in studying. They would then take these plates into a dark room, develop them and freeze that image in place, and produce this, pretty beautiful image of a distant galaxy. These seem like a sort of primitive way of doing astronomy, but most of the amazing discoveries that we made well into the 1980s came from photographic plates. I think this is a wonderful picture of this galaxy. You can easily see, the core of this little spiral galaxy and the nice little spiral arms. But you can compare the image from a photographic plate to the image that we get today with the digital cameras. So going from this photographic plate to an image taken with Subaru, the telescope that I was at the very beginning of the talk, you can see just how much more vivid and how much more dramatic this picture becomes. You can now easily see the nucleus of the galaxy. You can see bright blue knots of newborn stars. You can see dust lanes in red. The quality of image that we get is astonishing, and this doesn't break. You can easily copy-paste this into a new file and easily back up your data. You're no longer worried about dropping your thesis necessarily, or not as much. So people had a lot to say about the way that sheer technology and sheer tools were changing in astronomy. They also had a lot to say about the way our jobs are changing as a result. So this picture is of me standing at the construction site of a new observatory being built in Chile, the Rubin Observatory. So this observatory has a very simple but very amazing job. It's going to photograph pretty much the entire southern sky over and over again every few nights for 10 years. It's going to wind up giving us a movie of the night sky, of everything that's moved and everything that's changed over a 10-year period. And that is a huge shift over how we used to do astronomy, where we would watch stars one at a time, or keep an eye on little patches of sky one at a time to look for anything that's changed. It means that the volume of discoveries that we're going to make is going to be astonishing, but it also only does about half the work. It tells us that something new or strange has appeared in the night sky. What it doesn't tell us is necessarily what that strange thing is. This illustration here is an illustration of the research that I do and what I've been working on here at the University of Auckland. This is something called a Thorne-Tittkov object. We think it's a Thorne-Tittkov object in the process of forming. What it is a red supergiant, so a big massive star, something like Betelgeuse, swallowing the leftover dead core of another massive star known as a neutron star. So these tiny remnants of stellar cores that are supported by quantum physics rather than by the normal fusion that supports a star like our sun. We think, as is illustrated, that these stars form from very strange binaries. And I can quickly show you a video of how these stars would be born. You start out with two massive stars in a binary. The more massive star dies, it undergoes core collapse, and it produces this spectacular supernova explosion and leaves behind that neutron star. Then when the companion evolves and starts to cool off and inflate to become a red supergiant, it swallows that neutron star and leaves behind what we know as a Thorne-Tittkov object. These are very weird, bizarre types of stars. They were predicted to maybe exist for 40 or 50 years. And over time, we slowly started wondering if we could maybe find observational evidence that they're real. This meant looking for very strange stars, but then probing at them in incredible detail. I wound up doing this with some colleagues of mine at one of the big telescopes in Chile. We took spectroscopic data of the stars, where we basically took the starlight and sorted it out according to color. We got data that did not look like this. This is something that tends to surprise people when I talk about some of my professional observing data. I think they expect me to tell them, oh, we found this strange new type of star, and give them some beautiful picture like this. This was what our data looked like. And we were delighted. It looked awesome because every single one of those little streaks is a tiny piece of the star's light that's, again, been sorted by color. And by looking at little fuzzy dips or little bright dots, we were able to pick out some weird chemistry in this star that told us something strange might be happening. When one of my colleagues looked at this raw image, we didn't do anything to it. She was so used to looking at data like this that she immediately said, I don't know what that is, but I know that I like it. I don't know what's here, but I know it's something strange. By looking at these stars like this, we actually found a candidate for these weird objects where a red supergiant swallows a neutron star. We did this because we went to a telescope and did this the old-fashioned way. We pointed the telescope at stars one at a time. We counted on her expertise, having stared at data like this for years, to recognize what was strange. Studying stars like this requires these amazing brand new observatories like Vera Rubin Observatory. This telescope will be amazing at finding weird stars like that. It'll find stars that brighten and dim oddly. It will find stars that die as a supernova very easily. It will find tens of thousands of supernovae every single night. It will be a great first tool for doing these types of observations. But something people ask me a lot with telescopes like this is, are these going to start replacing astronomers? Are these going to start replacing the professional observing that we do now? Are these going to replace the work that amateurs do, studying how stars evolve and how stars change, and studying individual stars very closely? And the answer is overwhelmingly no. We absolutely need the power of a telescope like that, but we also need the traditional way that astronomy's been done. We need amateur observations. We need telescopes of every possible size. We need telescopes of every possible wavelength, radio telescopes that detect squirrels, telescopes that we put into the backs of planes, space telescopes. We really need the full range of stargazing tools that we have at our disposal in order to do this sort of work. So this is the argument that I try to make in my book, and that the answers that my colleagues gave to those questions really helped to support. Astronomy is evolving, astronomy is changing, the stories we have for it are different, and the adventures we have are different. The questions we're asking are still the same, and we still really need the full breadth of technology and the full breadth of people's curiosity to keep answering these questions. So on that note, thank you so much for listening. I'm happy to answer questions. I don't know how we're doing on time since we started late, but hopefully we're okay. Thank you.
What a fascinating talk. I wonder why you used the title The Last Stargazers, but I guess you're saying that it isn't The Last Stargazers?
Yeah, I actually had some colleagues ask me this because they were worried that the title was depressing or that I was saying astronomy was ending. And it's a little bit of a warning because, I mean, we're seeing this happen certainly in the United States with science funding, and you see this happening everywhere. It's really hard to get support for research and support to keep paying students. And people, especially as new technologies coming in want to do more with less. And I think if we're not careful, we could start seeing the last stargazers. We could start leaning too much on telescopes like this and lose the magic of telescopes like Sophia. Sophia recently got shut down because it didn't have enough funding to keep going. So I don't want us to be the last stargazers. At the same time, the number of students that we have studying astronomy at the University of Washington is at an all-time high. And there's certainly still plenty of people interested in doing this. So what I'm hoping is that we can sort of preserve the stories of how we used to do astronomy, but keep supporting this sort of research in the years to come, even as it starts to evolve and change a bit.
Questions from the audience?
That telescope on the far right-hand corner, does it not have an antenna in the centre of the dish, does it?
This one?
Yeah.
It has I think that's the receiver tower at the center, so they can change out different frequency receivers or different frequency horns. I don't believe that Green Bank has the ability to transmit. I don't think it has a transmitting antenna. Some radio telescopes do, but I don't think this is one of them.
Is it an aerial in the dish?
Huh?
There's no aerial in the middle of the dish.
No. Yeah. Huh?
First time I've seen it sort of thing.
Yeah, no, it's an unusual design for a radio telescope because the whole telescope can actually move and get driven around, and that's how it points itself, as opposed to the more traditional way where the dish sort of tips up and down or from side to side.
Okay, thank you.
Yeah. Yeah.
On your gravitational wave laser, how do they eliminate the background noise? I mean, you said there was a lot of it. How do they get rid of it? How do they know that it's a gravitational wave?
It's a great question. How do they eliminate the background noise and know that that detector is picking up gravitational waves? This was why that project took decades to do. They were painstakingly going through and eliminating every source of background noise one by one. Some of them are very predictable, so things like earthquakes, they are able to tell when an earthquake has happened and sort of delete data for that period of time. Others, they can easily subtract, so some sources of sort of latent noise, like the waves hitting the ocean shelf, they can get rid of. Others, they really had to get creative. So the way that the observatory works inside those vacuum tubes is they have very heavy mirrors that reflect infrared light because they're infrared lasers, and the mirrors have to sort of hang loose so that if a gravitational wave arrives, they sort of swing and move a little bit forward and backward as the wave passes. The way that they have hung those mirrors alone, that one little detail of the observatory, has been years of engineering to eliminate noise as much as possible. Because if you imagine a mirror with a hole in it hanging on the metal wire is going to scrape a little bit or creak a little bit going back and forth, and that would cause errant signal. Even if you make a perfect wire, the atoms in the wire have a sort of base chaotic motion, and that motion will create noise. They now hang these giant heavy mirrors on little glass rods that are specifically blown because the structure in glass is able to minimize that sort of noise. That's just one example. They have about 24 more examples of just how astonishingly carefully they've engineered every inch of that facility so that it is as immune to noise as it can possibly be. I think it's the most amazing engineering that we've done since the space program, since we landed on the moon. It's amazing that they can do this. I hope that somebody writes a book. There have already been books written about that whole project, and I hope someone specifically writes a book about the engineering challenge of it, because it's dazzling. Yeah.
So Green Bank can't transmit, Goldstone can, presumably. Is Goldstone bigger or smaller? Another question, do you think it'll ever rebuild Arecibo?
Oh gosh, yeah. So I'm not familiar with Goldstone, but I would assume it's smaller. Green Bank is the largest drivable telescope in the world. It's 100, what is it? Is it 100? It's either 100 meters or 300 feet. I don't remember exactly which one it is, but it's about that size. I desperately hope that they do rebuild Arecibo. I'm guessing most folks here saw footage of the Arecibo collapse. So what's heartbreaking is Arecibo collapsed in, I think it was December of 2020? Yeah. And I was writing this book in 2019 and planning the trips that I needed to take for research. And I was able to take 4 trips, and the 5th one on the list was Arecibo. And I said, oh, I've talked to so many colleagues who have been there. I'd never gotten the chance to go. I figured I'm not going to get to go for this book, but it's Arecibo. It's so famous. I'm sure I'll get to go there someday. And then it collapsed. It's one of the, much like Green Bank, it's one of the most amazing places we have for radio astronomy. I'm desperately hoping that they will rebuild something there. It no longer, again, has the financial support it needs to keep going. So that was a bit of a Last Stargazers depressing interpretation situation, but I'm really hoping that they're able to find funding to either rebuild something like Arecibo or at least reuse the site to keep doing radio astronomy. It would really be a shame if we lost that place and that capability, so hopefully.
There is a similar telescope in China now.
Yes, which is now bigger than, I don't remember exactly how big it is, but it's beat out Arecibo as the largest radio telescope, period. So we need more of those, but it would be great if we could get this one in Puerto Rico back. Other questions? Yeah.
You've obviously seen a lot of history about observing and where it's been over the last, 100 years maybe. Where do you think it might head in the next 100 years?
Next 100 years.
Oh, well.
Yeah. No, if I can dream big, I would love to see us put more of these telescopes on places like the moon. We saw our little 4-inch telescope on the moon. Imagine something like Arecibo on the moon. And then imagine we're very good with radio telescopes at synchronizing them. We've actually synchronized radio telescopes to make an Earth-sized telescope. This is how we took that infamous picture of a black hole. So imagine what we could do if we had an Arecibo on Earth and an Arecibo on the moon that we could actually use together. I would love to see us do that. We're going to see a lot more space-based astronomy. Webb is already taking amazing new observations. We have plans for next generation and next generation space telescopes. And we're going to see a lot more automation along the lines of Rubin. This telescope is going to get, I forget the exact number, but it's on the order of, 40 petabytes of data in a month from Rubin. So I heard all the computer scientists go, ooh, because it's just an absurd number. But that's now getting into the point where things like machine learning and things like artificial intelligence become useful research tools because they can tear through in moments what would take students weeks. And the trick, of course, is not letting the sort of rote work of AI replace the creativity of somebody looking at this data and having an unusual question. But we're going to wind up sort of combining a lot of these tools in the immediate future, let alone what's going to happen further down the road.
I just had a question about Sophia. Do you think one of the reasons it was shut down was because of the Webb telescope becoming online, because people would argue, well, we've got a big infrared telescope in space now?
I do think that was part of the reason, and I think that's a shame, and I think they're wrong. Because, yes, Webb is an amazing infrared telescope. Sophia also covers the infrared, and covers the infrared in some cases to a different wavelength range than Webb. It goes much redder in some cases, to much longer wavelengths. It also is unique because it's much smaller. There are certain observations that you can only do with a relatively small telescope. I have colleagues who talked about pointing Sophia at something like Betelgeuse, which is way too bright to point Webb at. They would never let us do it. And I really think that we lost an important observational niche when they canceled it, which is too bad, because I think they did think, oh, well, Webb can do everything Sophia can do, and it's not true. I'm really sad that it stopped.
Tracy, did you have a
No,
question?
I was actually going to say the same as what Emily said about the bandwidth. So.
Yeah.
Okay.
Mm-hmm.
Yeah.
Yeah.
Okay, thank you. Before we finish, in that case, I'd like to thank Emily again. I've got a small gift to send on behalf of the society.
Thank you.
Thanks for that.